And as you can see, I have a lengthy title, but no worries, I will explain it in the coming slides. So as an introduction, I want to show you this snapshot of our modeling metrics, and most of the modeling requests that are taken up are ad hoc requests, of which the largest category is related to vapor-liquid equilibrium. So it's the same category as where the solvent switches belong to, and this is not surprising since modeling of solvent switches is straightforward, and thanks to pre-made solvent models, such as the well-known Unifac activity coefficient model, solvent swap modeling pays back well. So we wanted to move away from that ad hoc behavior and change it towards an embedded and integral workflow in which modeling is meshed with the data generation. So basically, that is how the Solvent Switch project got initiated. So the Solvent Switch project was being constructed more than a year ago, and from a business perspective, its objectives were on the organizational and operational level. So from the organizational level, we wanted to deliver a standardized approach in which models and PAT tools were a crucial part of. And we also wanted to challenge our organizational readiness for future, perhaps less straightforward, model-based approaches. On the operational level, well, we obviously wanted to have optimal processes. We saw that previously a lot of solvent switches were transferred suboptimally, and we wanted to move to less solvent usage and of course still delivering robust processes. So if you combine both the organizational and operational deliverables, you understand the title of this webinar. The calculation of the accumulated distillate compositions, and also a condenser energy balance calculation was added. Regarding the modeling capabilities, we were very much looking to expand the NRTL interaction parameters because, yeah, since it was not feasible to work with the modified Unifac model, we wanted to be able to create more accurate simulations via NRTL. We also included the capability to train the solubility of a solid material, so for example the product of your synthesis. And we also included the dynamic calculation of density. Regarding the more rigorous endpoint detection, we included a boiling point correction that was already present in one of the other DynoChem templates, and we included the refractive index calculation. So this is how our user input sheet looks like. So in the center frame, you define the starting compositions and the conditions of your vessel. So you define the pressure, the starting temperature, and your bill of material for solvents. And we have, I will show you in the next slide, there is a zoom in. You will see later that we have expressed it based on the limiting reagent of your recipe. We regress the solubility via one of the 6 solubility expressions, and the resultant solubility curves are shown here. So that will then be copied. So you copy the 4 parameters of that specific solubility expression into the solvent switch user input sheet. You see that we have selected expression 1 of the regression tool, and we also need to specify both solvents that took part in the regression. And at the upper right, you need to select which plotting options you want regarding the solubility. On this slide, you see how the simulation looks like. So for the calculation of the refractive index, you have 9 or 10 equations. We have taken the Lorentz equation, and it makes use of the refractive indices of the pure solvents and their volume fractions in the mixture. in the graph, you see that the temperature is in green again. You see that the weight percent acetonitrile increases in the bulk, and that its presence is in the vapor. It follows a similar trend. And the purple and the noisy blue lines are an overlay of the predicted and the measured refractive index trends. It's not the best experimental curve, I know, but it shows that it is feasible and that you have an additional control measure